Newton described the effect of forces to be that they cause a change in motion. In Latin, Newton used the word momentum for motion, which is a reference to the momentum of an object that Rene Descartes had given a definition, and that definition is written there as P is equal to mv. So it turns out P is actually the symbol for momentum. May seem a little strange, but it is what it is. The question says they'll use the statement that the net force equals a change in momentum to derive the more common modern form of Newton's second law. So if you kind of look at the statement we have on the key concepts slide, that was a direct translation of Newton's statement of Newton's second law. He really, you could interpret it as saying that net force equals a change in momentum. In other words, what if you started, instead of saying, like I've claimed that that's the same as F equals ma, but what if you said, well, let's use Rene Descartes' definition of momentum, and instead of starting with F equals ma, let's say that F net is equal to a change in momentum. And the way I'm going to write that, because like here, I could say F net is equal to a change in momentum P. Triangle generally means change always, right? In science and in other places. But really, I think I should look at this as like a change in momentum over like, some time interval. So maybe I'll just put that over a time t. Maybe I could have called this a delta t, but maybe it doesn't need to be a delta t. But now if we think about this momentum, right, because we're talking about change in momentum, but if I say, okay, we're talking about a change of a mass times a velocity, because that's the definition of momentum. We'll do a chapter on that in the future in this class. And that was the definition that Rene Descartes had originally set down for the momentum, which was meant to be a measure of all the motion of an object, and in that sense included not just how fast it was going, but it also included the direction it was going, hence the vector here. But in addition to that, it included how much matter there was in the object. In other words, how much mass. One could argue that maybe Rene Descartes really got us started with this idea of mass, kind of separate from the idea of weight, really. But if you look at this, you kind of say, well, what's the change of a mass times a velocity? Well, if it's an object that is just changing its velocity, you could interpret that as just the mass times that change in velocity. And maybe it's a little bit of a cheat. There's kind of, in math classes, there's maybe a more formal way of doing what I just did. But we're going to argue, hey, the mass doesn't change. So if I'm talking about a change in object's momentum, that's going to be entirely reflected in a change in the object's velocity. And maybe I was jumping the gun a little bit here by shortening that line. But, that's maybe what the next step could be, is like, algebraically, I can do that, right? If I have m times delta v over t, I could turn that into m times a fraction of delta v over t. But what's the interpretation of delta v over t? This is change in velocity over time. Oh, wait a minute. I think we've seen that before. That's the definition of acceleration. And so in that way, I've arrived using this concept of momentum at F equals ma, which is kind of how we usually present Newton's second law in the first place in modern times. So there it is. There's the answer in the slide, and it looks pretty similar to what I just did.